I forgot exactly where I stopped last time. But we were doing this example of a mixture problem. So you have this A here, this path A and path B, 10 liter per minute, 4 kilogram per liter, and this is 8 kilogram per liter. $500 liter. This is coming out also at 10 liter per minute. So initially 20 kilogram of salt in the tank. So you start with valve A at T equal to 5, switch to valve B. And then we set the thing up, and I think I was right here. Is that correct? Last time I stopped here? Can you guys tell me when I stopped here last time?
Yeah, you stopped there, or the line just after, when you had taken the Laplace transform of both sides.
Oh, I did. Okay. This 20 is coming from there. Okay. Okay. So I stop roughly around here. So what do we do next? So we need to isolate. We need to isolate this ys thing here. So it will be s plus 1 over 50 ys equal to this 20 move to the other side. So ys will be, so from here is just computation. So after all the computation, I'll just try to explain to you, hopefully give you a little bit insight at the end, okay? Okay. So we get to this now. What do we do? So this one is not too difficult to do. Then what do we do with these other guys? So what technique do we need to use? We need to use something called partial fractions to separate them out. Okay. So I need to know that 1 over s plus 150. If you go through the partial fraction, you are going to get, you're going to get this 50 over s minus 50 over s plus 50. Okay. Yeah, that's correct. This is just a process of partial fractions. You have the a and b both equal to 50, it turned out. Okay. So we just replace this. So 40 plus 40 e to the power minus 5s 50 over s minus 50 over s. Okay, I'm really sorry, just really long this thing. Okay, but I think we have it correct there. Are we okay up to here? You notice that those are one entity because both of this has the e to the power minus 5s over there. So over here, these two terms can be combined, right? Is that right? Those two guys can be combined. So the first one I have 40, 50 is 2000 over s minus 40, 50 you 2000, but you have plus 20, 1980 s plus 150. Hopefully you still understand what I'm doing. Now the 50, I'm going to take it out. I end up with 2000 e to the power 5s 1 over s minus 1 over 50. And I need to take the inverse transform of all this stuff. Okay, so IT. What is the inverse transform of the first one here? Anyone? What's the inverse transform of 1 over s?
Just 2000.
So this will be just 2000. Okay, minus 1980 s plus 150. Inverse transform
negative
of
150.
is negative 150 t. Okay, plus this guy, which is 2000. Now it's these two guys, but then you multiply by this, that means there's a shift. Okay, so you basically take the inverse transform of this guy first. Okay, each of this. Now this one is 1 over s, which is 1. Okay, so this 2000 is still here. Oh, this is the 2000 plus 2000. The 1 over s become 1. This guy become e to the power minus 150 t. But I need to shift the t to t minus 8, which is 5. to t minus 5. Okay, and then I need to multiply this whole thing by u. Okay, I'm running out of space. I'm going to write this smaller then, okay? 1 minus e to the power minus 150 t changed to t minus 5 u t minus 5. I think that's correct. Okay? So at the end, I have 2000 minus 1980 plus 2000. 1 minus e to the power minus 150 t minus 5 here. Okay? And then u t minus 5. So that is the result. Okay? So basically, this can be written in two parts if you want to. Okay, if you really want to, you can write this as a piecewise function. Okay, two parts. The first part is when t is between 0 and 5. Okay, t is between 0 and 5. Between 0 and 5, what do we have? We just have this first part. Okay, you just have this first part. And then later, which is for t bigger than 5, you are going to have both of them. You're going to have both of them because these guys, at the beginning, it will zero this guy out, so it's only have this part. Later on, you have both parts. Okay, this part is always there. This part is always there. So the second one is just copy the whole thing. So this one is still there, and then you add this one. 1 minus. Okay. So that's eventually the answer. It's very tedious. Okay.
Wait.
Oh, I shouldn't erase that picture. Oh, sorry. Okay, so how does this graph look like? Graph, okay. At the beginning, so this is t, this is y. At the beginning, you're with 20, with 20 kilograms. Okay, when t equal to 0, you get 2000 minus 1980. And then it starts to just keep moving up. Okay, it's keep moving up. Okay, and then there's some kind of discontinuity at t equal to 5. Okay, because later on, originally was the concentration was 40 kilogram per liter. Later on, it's 8 kilogram per meter, so it's going to go up like this. Okay, and as t goes to infinity, you can probably see what happened. It's 4,000. As t goes to infinity, this will become 4,000. We have this line here. This is 4,000, which corresponds to the 8. Which corresponds to the 8 kilogram per liter, and the original capacity of the tank is 500 liter. It's the product of these two numbers, which get reflected in here as t goes to infinity. Okay, this is 0 and this is 0. Any questions, guys? It's a lot of calculation. It's just the numbers doesn't come out that nicely because I just make up those numbers last time. If you have no questions, I'm going to go to 7.5. I'm going to go to 7.5. Unless you have a question. Okay. 7.5 is the final section for this semester. So after that, we will just do review. So next week is definitely no new material next week. Okay. So we have learned quite a bit though for this class. It's a lot. So we'll do some review next week. This is a name pronounced as Dirac. It's a Dirac delta function. Okay. Dirac delta function. This is defined like this. This is, do you guys know this is the Greek letter delta? Delta. Yeah. Alpha, beta, gamma, delta. A, B, C, D. This is D. Okay. Delta A. T minus T0. Okay, it's a lot of writing there, but geometrically, this is what happened, guys. You have this point here, T0, some point here, T0. Okay? And then you have T0 plus A here. You have T0 minus A here. Now, what this function is saying is the following. It's 0 outside here, 0 outside here, okay? But in between, in this interval, this length is 2A. This length is 2A. This is 1. Okay, this is what this describes this curve, this graph. What do you think is this area here? The green area. Oh, that's not 1, sorry. This is 1 over 2A. What would be the green area? This height is 1 over 2A. And the width is 2a. How do you compute the area of a rectangle? So what do we have?
1.
It's 1. So this guy is 1. Okay. Now, this function here, t minus t0, is called the Dirac delta function. It's actually equal. This one doesn't have the a here. That one has the a there. Lemon delta a t minus t0, a approach 0. Now I want you to imagine this. I'll show you some animation later. I want you to imagine this as this a gets smaller and smaller. The a gets smaller and smaller. Then I will have this guy, let's say a is a little bit smaller, then this guy will be taller, right? Is that right? You guys know what I'm talking about? Because the height, you maintain the area equal to 1, but you have this a getting smaller and smaller. So the height will have to get bigger and bigger to maintain the area of 1. So conceptually or intuitively, this a go to 0, the height go to infinity. Okay. This is not really a function. It's a really strange function. It's called generalized function. It's discovered by the engineers. Mathematicians later on put in a theory around it called theory of generalized functions. Basically, what it's trying to do is to model an impulse. Okay, this is an impulse that's really the height of the function is like basically infinite, but the time, that duration is very short. So it's like when you hit something like this, that is an impulse, and that is the Dirac delta function. Okay, I am going to share my screen with you and show you some, essentially show you this animation. Hopefully you already understand it. Dirac delta function. Okay, here. Can you guys see my desktop?
Yeah.
Can you see what's going on? The animation?
Yeah.
So this is when A is pretty big, and then now A is going to go smaller at some point. Yes, A is starting to go small. A is approaching, when A approaches 0, that is the Dirac delta function here. It popped all the way up. Is it okay? So that is the concept. So that is a very during a very short period of time with a very high amplitude. So here, this A is getting smaller and smaller. Okay? Keep going, right? You understand what I'm talking about. Okay? That is what we are trying to model. Modeling an impulse. Any question? Before I unshare the screen, stop sharing the screen and then talk about the Laplace transform of the delta function. Okay. So intuitively, this is what you should think about. This is what happened. This function, you remember that that's a unit step function. That's a unit step function. This guy looked like this. Here is A. You go up a step. You go up a step. Okay. These are the okay. Think about taking the derivative of this function. If you take the derivative of this function, here you have a sudden jump. So the derivative here is 0. Derivative here is 0. But right here you have a sudden jump. It's discontinuous. You really cannot do the derivative. But basically, if you differentiate this guy intuitively, this is dealing with this so-called generalized function now, because it's not really a nice function. Basically, this guy here, you should think about this as the derivative of this. Okay, so it's basically differentiation. You'll get this integration. You'll get the other. Okay. When you integrate something, let's say you have a, I have a function y equal to x squared, right? When you integrate this, you have x cubed over 3. That's constant. So one way to think about this integration, is you are actually talking about area under the curve, right? As you move this point, here, keep moving it, you accumulate more and more area. Okay, that's the concept of integration. So you can think about it this way. So you accumulate more and more area under the curve. So if you think about this guy, which is this spike here, this is a delta function at this point A. Okay. So as you do the integral, so you try to accumulate area under the curve. So as you move along here, the area is 0, and suddenly the area jump to 1 because the area here, this spike is 1. The area jump to 1, and you keep going because this is 0. The area of 1 is not going to change. It just maintain at 1. It will be exactly look like this. So intuitively, the derivative of the step function is the delta function. The integral of the delta function is the unit step function. Okay? So that is the intuition. So based on this, we can do the following. Let's do this. You guys remember the derivative? You have this picture. You guys remember this picture? Maybe I won't do that picture. I'll just do it directly from definition. Okay, so it's a theorem. Laplace transform of this guy. Okay, let's compute the Laplace transform of this guy and see what it is. is saying that it's equal to this. Okay. Let's try to figure this out. Okay. What's the Laplace transform of this? I'll talk about the significance after we finish this computation here. This Laplace transform is the definition of Laplace transform. Okay. Definition of Laplace transform is going to be from 0 to infinity. E to the power minus st delta t minus t naught. Okay, so that is just a definition. That is just a definition. Now this definition here, because this guy here is going to be 0. Let me just redraw the graph then. How does this look like, this function? The graph of this function look like this. Okay. You have a here, you have these two sides, a plus t naught, a minus t naught, sorry, the other way. T naught here, t naught plus a, t naught minus a. Okay. I have the a here first. I'm going to do the a here first, and later on, take the limit as equal to 0. Okay, so now we have this. So this is 0 here, and then you have some value up here. Okay. So most of these are 0, so I can change the limit of integration. Okay, from t0 minus a to t0 plus a. Do you guys follow that? Okay, so this one will be this. Now this guy here, this value is 1 over 2a dt. Hopefully you follow that. Is it all right?
Professor, what do you have on the integration second to the last line? Is that 0 to infinity? Is that what I mean?
And that's the definition of a Laplace transform.
I know, but is that infinity or is the second to the last line?
Here.
Up. No, on that integral, the limit of it, is that 0 to infinity?
Yeah.
Okay.
You're asking me where does that come from?
Oh.
Is that what you're asking, Antonio?
Yeah, I just couldn't read it.
Yeah, it's an infinity.
Okay.
Yeah. Did I answer your question?
Yes.
Are you asking me why is that 0 to infinity?
Sure.
I cannot hear you well.
He said yes, you answered his question.
I do, okay. Yeah. Okay, it's 0 to infinity. So this is a definition of Laplace transform because Laplace transform of f of t is equal to integral 0 to infinity this guy f t dt. Okay. So we end up with this now. I eventually will want a go to 0, okay, but I have to compute this first, okay, and then I'll let a equal to 0, and then I'll end up with this, okay, and I will end up with this. Okay, so what is this? This guy I can take the 1 over 2a out. Okay. What is the antiderivative of this? Will be itself adjusted by negative s. Okay. And then you have to evaluate at here and here. Is it okay? Then you plug this guy in, the upper limit and the lower limit. It's just a bunch of tedious calculation, guys. The whole thing divided by negative s. Okay. We all right. So what do we have here? We will have some common factor here. Can you see that e to the power minus st naught is going to be common? Okay, so I'm going to take that out. E to the power minus st naught. That is being taken out. What remains is going to be e to the power minus sa subtract e to the power minus would be plus sa. Okay, divided by negative 2 as. Okay, that is the Laplace transform of this guy. Now next, I actually need to take the limit as a go to 0 because I want the function which has the spike. Okay, so we're going to take this limit as a go to 0. Any questions so far? This is just a bunch of computation from the definition of the Laplace transform. We are going to take the limit. Okay, the Laplace transform of this guy turn out to be the limit of this expression as a go to 0. And what is that expression? When a go to 0, what happened here? What happened to this top and bottom? When a go to the 0, what happened to the top? It's 1 minus 1.
0.
1 minus 1, not 1 plus 1. The top is 1 minus 1. A go to 0. 1 e to the power 0 minus e to the power 0. The bottom
It's also 0.
is also 0. So when you take the limit, you have 0 over 0. What
Do
do
we
we
use
do?
L'Hopital?
We use L'Hopital rule. Use L'Hopital rule. Now when we use L'Hopital rule here, okay, we're using L'Hopital rule. We have to differentiate the top and bottom. With respect to what? Differentiate the top and bottom with respect to
S?
not S,
Oh, A, sorry.
with respect to A. So I'm going to differentiate the top and the bottom with respect to A. Now the bottom differentiate with respect to A. Yeah, am I missing a minus sign here? Am I supposed to have a minus sign there? Yeah, I didn't.
Yeah.
Okay. I do have a minus sign there, right?
Yeah, you do.
Yeah. Okay. With respect to A, this becomes negative 2s. Now the top with respect to A, remember, with respect to A, the derivative is itself. Okay. It's chain rule, so you have a minus s in front. Okay. minus, take this derivative with respect to A. All right. So it's itself with a s in front. So now we have limit equal to 0. This is minus 2s e to the power minus sa minus 2s. So when a equal to 0, what happened to this? When a equal to 0. That guy goes to 1. So we have e to the power minus st0. Okay. So that is our Laplace transform. Okay. So we have shown that this Laplace transform here of delta t minus t0, which is this function with a spike here. Okay. T equal to a. You have this spike. The Laplace transform of this guy is just equal to e to the power minus t0. Okay.
Professor?
Yes.
The e to the negative SA and e to the SA, it cannot combine together, right? For the third light?
Oh. They cannot combine together. Or maybe not yet. Yes. So, yes, you are right. Minus s e to the power minus sa minus e minus s e to the power minus sa plus e to the power. Thank you. I think I messed up. Okay. But it doesn't change the conclusion, luckily. Okay. When a go to 0, I have minus 2 and then 1 plus 1. Minus s 1 plus 1. Okay. So I still get the same answer. Okay. Thanks for pointing that out. Yeah. I can combine them. I mess up here. Okay. One is minus, one is plus. So you get to this. When you take the limit, both of these become 1. Okay. So it's the same conclusion. Yeah. Thanks for pointing out the mistake. So okay, so we have this. So what do you think is the Laplace transform of, okay, so what happened when t0 equal to 0? Now when t equal to 0 equal to, oh, this is t0. When t0 equal to 0, what happened? So the spike is right here, okay? The spike is right there. So this guy will be, this is the Dirac delta function with the spike at time 0. So that means at time 0, you hit it with the impulse. So what will be the right hand side? When t0 equal to 0, this guy will be, what will be this?
1.
It will be 1. Okay. So the Laplace transform of a spike, okay, unit impulse. This is a unit impulse. The area is 1. Okay. At time 0 is equal to 1. So the inverse transform of the constant 1 is going to be this. Okay. So this is these are the stuff that you need to know, okay, when you work on the differential equation problems, okay. Okay. Okay, good. We can do some problems now. We can solve a differential equation. Any questions so far? So these are useful. Okay, let's try to solve this. Before we solve it, I want to talk a little bit about what does this mean. This part here is a simple harmonic motion. Okay, this is the case of a spring. There's no damping because there's no y prime term. Okay, and if you look at the characteristic equation, you'll get you the sine and cosine. Do you guys recognize things like that? The characteristic equation is m squared plus 1, and then you get plus or minus I. Then you get cosine and sine.
Yeah, that makes sense.
Yeah, okay. So, but in this case, you can think about a spring. A spring. Here, initial position is a little bit off. It's not the equilibrium position. This one say that you're not pushing the thing, you're just releasing it from rest. Okay. So you can think of it as a spring here, as a spring with this support. This is the equilibrium position, but you put this down a little bit. Okay, put this down a little bit to here, and this distance is 1. And you're just releasing it. Okay. But when you release it, okay, that's fine. It will just do its own thing. So you know basically roughly how it looked like. You release the spring. Okay. So originally this is 1, and then it's going to go back, and then it's going to go. It's a sinusoid. It's probably going to bounce like that, right? So at the beginning, it's going to bounce like that. Simple harmonic motion. Okay. But suddenly at time t, this is saying that at time t equal to 2 pi, you hit this with an impulse. Basically, you use a hammer to hit it. Okay, how hard do you hit it? With a magnitude 4 times the unit impulse. Okay, that means that spike that we talked about earlier, here's 2 pi. That spike we talked about there will have area 4 instead of area 1. Okay. Of course, when you hit it like that, it's going to change things around a little bit, right? Because you suddenly jerk it by hitting it with a hammer. So we're going to solve this. Okay, we're going to solve this, and then look at the graph of the solution. Okay? You guys understand the setting? It's a mass spring system with no damping. Okay? That's why with no damping, it's going to be simple harmonic motion. But somehow at t equal to 2 pi, this curve is going to change shape. We're going to see what happened to it. Is it all right?
Yeah, I think so.
Okay, so we can do this. We have yt, which is ys. And here, it's going to be y prime t. Will be sys minus what?
Y0.
Which is 1. Okay. So sys minus 1 plus ys equal to the Laplace transform of this guy. 4 times the Laplace transform of
Professor,
this. Yes.
isn't it Y double prime, not Y prime?
Oh, y double prime. Jesus Christ. Thank you. Thank you so much. Okay. Y double prime. Okay. Y double prime. Okay. All right. So what do I do here?
S times Sy of S minus 1, and then you would subtract Y prime of 0, but that's 0.
Yes, it's exactly. Thank you so much. Okay. So now I have this whole thing. Okay. S ys minus 1 plus ys is equal to the Laplace transform of this is 4 times something. 4 times what? E to the power minus s times t0. Where's t0?
2 pi.
2 pi. Minus 2 pi s then, okay? Okay. And then the next step is what? The next step is to get these terms together. S squared plus 1 ys will be minus s equal to this, I believe. Okay. And I will have ys will be s plus this guy divided by s squared plus 1. Is it okay? And then my yt will be the inverse transform of this. What is this first one?
Cosine.
That will be cosine t. Now the second one is 4 times. It's 4 times cosine t, except that because of this guy, we have some kind of shift. Okay, so if you look at this, you remember this ft fs e to the power minus as fs. If I remember correctly, no, not f prime. Sorry, I have to look at this. When you have this side e to the power minus as, the other side is f t minus a ut minus a. Is that correct? I hope it is. I need to check my notes. You remember the diagram, second translation theorem?
Yeah.
Is that correct? I think it's correct.
Looks about right.
Is it good?
Yeah.
Okay. I wasn't sure whether there's a minus sign here. Okay, so that's good.
I have a question.
Yes.
For the second term for y of t, why did you get 4 cosine t instead of 4 sine t?
Oh, maybe it's 4 sine. I don't know. Yeah, it's 4 sine. Yeah, you're right. It's 4 sine. 4 sine t. Because there is no s there. Okay. 4 sine. Okay, let me just work on. We can work on this and then see what that thing is. Yeah, you're right. So we have 4. So this guy is 4 times s squared plus 1 to the power minus 2 pi s. So a is equal to 2 pi. Okay, a is equal to 2 pi. So this one is 4 s squared plus 1. Okay, so this one is 4 sine t. Okay, so you got it. Okay, so it will be 4 sine. Okay, 4 sine t. Except that we have to move this guy to what?
T minus
Replace by t minus 2 pi,
2 pi.
and then u t minus 2 pi. Okay. Yes. Thank you. Yeah, that was a sign. Okay. So 4 sine t minus 2 pi u t minus 2 pi. But what is that? What is this t minus 2 pi thing? Can I simplify it?
Sine t cosine 2 pi minus cosine t sine 2 pi.
Yeah, you can do that. Yes. But
And
you
you
can also just, the period of sine is 2 pi, right? So you subtract one period is itself. That's another way to look at that. You see what I'm saying, Donna?
Yeah.
Yeah, because the period is 2 pi, so just shift by one period. Okay, so we got this. And now we can graph this. Okay, roughly see what this looks like. So what this is saying is the following. What this is saying is that yt originally at the beginning is equal to cosine t. Okay, it's equal to cosine t if t is less than 2 pi. That means at the beginning it's just following that curve I drew earlier and then erase the simple harmonic motion at the beginning. But suddenly when you hit it with a hammer, it's going to change. It's changing to not just the second term, but the second term together with the first term. Okay. Is it all right? Does it kind of make sense?
Yeah.
Now this guy here, you have 2 waves. You have 2 waves, same frequency. Linear combination of 2 sinusoids with the same frequency. You can write it in terms of yet another sinusoid. You guys kind of remember that? Do you know what I'm talking about? No? You have A cosine t plus B sine t will be equal to A squared plus B squared sine t plus phi. You guys remember that we have a way to figure out the phi? Yes, no? Is it coming back a little bit to you? No? Not at all? Okay, we have 10.
A little bit.
Okay, so we have 10 minutes. So why don't we just even do this? Okay, we're going to combine these two. Then it can explain the graph a little bit better. Okay, eventually I'm going to show you the graph. I have the graph. Why don't we just do this? Okay, so okay, here's what happened. When you combine two sinusoid, one is sine and one is cosine. As long as they have the same frequency, this can be cosine 5t, as long as the other one is also 5t, it will work. Okay, so this one is some constant c times sine t plus some angle. And you can figure out what the angle is and what the amplitude is. Okay. Yes, so we have c sine t cosine phi plus c cosine t sine phi. Okay. This is just the sum of angle formula. Sum of angle formula. So if you compare this guy and compare here and here, you can see that A, okay, you have, can you see that A is A cosine t. See the A cosine t? A is equal to C sine the angle. B is equal to C cosine the angle. Can you guys see that? Are you able to see this?
Yeah.
Okay. So from this I can recover the angle. I can recover the angle and the C. C is the amplitude. So you square both sides and okay, this is 1, this is 2. 1 square plus 2 square will give you A square plus B square equals C square. Okay. The angle is going to use 1 divided by 2. 1 divided by 2 tangent phi is equal to A over B. Okay. So phi is actually equal to tangent of A over B. But sometimes this is in the wrong, it's not in the correct quadrant, and you have to bounce it or it's equal to either this one or this one. Okay, so for our situation, here, we have what? 1 and 4. A equal to 1 and B equal to 4. Okay. So both A and B are positive. Both A and B are positive. C is positive. So sine is positive, cosine is positive. So this is the first quadrant, okay? So my magnitude here. So this thing here, I'm gonna write it here. Equal to cosine t. T is less than 2 pi. Now this one I'm combining them. So this will be 1 square plus 4 square and then square root is the amplitude. It will be square root 17. Okay. And then sine t plus some angle. What is that angle? How do I get that angle? That angle is arctangent of A over B. Okay. A over B, arctangent of 1 quarter. Is it okay? And that is in the correct quadrant. I don't have to adjust it by pi. I don't know how many radians is it. I don't have my calculator. So I'll just write arctangent. 1/4. Okay. So at the beginning, it's just the cosine function. Later on, it turned into another sinusoid with some shift. Okay, with some shift of phase shift. Okay, so because of the hammer is hammering at the thing, at the spring. So I am going to show you the picture. Okay, can you guys see that?
Yeah.
So this guy go along here. If you don't hit it with a hammer, it will just continue. It will just continue. And because you're hitting it with a hammer, can you see that the amplitude become a lot bigger now? Okay. It become a lot bigger. Okay. Because you're hitting it with a hammer. And we actually get square root 17, which is pretty good, right? Yeah. Yeah, which is around 4. Yes?
Yeah.
Okay, so that's really what I have. Okay. So I do have another picture here. This picture corresponds to the other to a case where at the beginning, this picture corresponds to a situation where at the beginning, it is not released from the, at the beginning, you release it from the equilibrium position for this picture. Okay. If you release it from the equilibrium position, nothing is going to happen. You know what I'm talking about? Nothing is going to happen. You have a spring in the equilibrium position. You just release it. You're not hitting it with anything. So it's not changing. And at 2 pi, you hit it with the hammer and you get to this. Okay? Any question? Okay, so I think that's all I have. And I essentially finished this section already. So we actually have a lot of time to do review stuff. So we actually have 3 more classes. Okay, so we'll just start to review stuff. Okay, starting on Thursday. So, did I publish the study guide for you guys?
Yeah, you did.
Yes.
Yeah. Okay, so I mean, if you have questions about that, you start well on it. We can spend time on entertaining questions. Okay, I do have some stuff I can review with you. Okay.
How many questions will it end?
I cannot hear you.
I was saying, how many questions will it end up being?
Oh, on the exam, I think it's 10 questions. I think it's 10. Maybe, I think it's 10. I'm not 100% sure. Okay, I'm not sharing screen anymore now, right? I can actually look at it and see how many questions.
No, you're not sharing the screen.
Okay.
I mean, you can if you want, but
Okay.
nah, I'm just joking.
I know you're joking. That's why I asked you whether I'm sharing the screen. That's why I asked you. All right, let me take a look at how many questions are there. Yeah, it's 10 questions. Okay? It's altogether 10 questions. it's it's going to be a little bit harder than last time, right? Because last time was in web assign. Yeah.
Yeah.
So just
And
want
you
to.
said you were gonna curve, correct?
I'll curve it. Yeah. Yeah. I will curve it. Yeah. Yes. Yes. Exactly. The goal is to make it harder, but then curve it. Yes. So don't get panicked if you don't do too well. Wait for the result first. Okay. But wait after I grade. Okay. So you guys learn a lot, and then on starting Thursday we will do some. I have some stuff I have prepared that I can review with you, and then after that we can maybe open it up for questions next week. So
Do you have any like suggestions on, say, like I guess like some people have like Patrick JMT, like videos that would, or sources for other content besides like Khan Academy that would be good?
I don't really for this
Oh,
class. I mean, there's stuff that I have done. Was really useful for me. There was it MIT or Yale? I mean, I think there was a set of video that I used, which was really good. I think it might be MIT. Yeah, it might be either. Is it MIT? Yeah, ex-MIT. There's a set of MIT has a class on differential equation, and it's really good. But I'm not really sure whether that's the best way to prepare for the final though. It's a very good way to learn. I learned a lot from those videos. I actually use them. I mean, I would spend like the summer just watching the whole thing. It's like a lot of lectures.
so you were saying that since last time it was more of what was included in the book, but this time for the final it won't be. Wouldn't the ones that you have listed in the study guide, um, would those then not be a good source of
Oh no, that's
studying
still
per
the
se?
best source. That is still the best source.
Okay, because I mean, like if they're not going to be, well, I mean, I guess they really can't be too much. Basically, are you saying that those are more of just this is the style? Problems that you might see?
Okay, so here's the process that I prepare this final exam and the study guide. Okay, I'll just tell you. I used to just take some problem from the book. Okay, without the lockdown, without the shelter in place, my style is that I'll just pick some problem from the book. But because now it's open book and open notes, everything open, I cannot do that anymore. So I will make up some problem, okay? And also when I make up the problem, I usually have to put it into Google search to make sure that not exactly the same problem will come up, okay? And because, so the wording and so on will be slightly different from the books. But I still make up the test first, the exam first, and then I look at the problems. I look at the problem in the test, and based on that, I chose the problems in the study guide. Okay, so that the concept that is needed to answer the questions is covered by the study guide. Does it kind of make sense?
Yes.
Does it help you to understand how to prepare? I mean, the best way to prepare is still the study guide. But the main thing is that when you try to study the study guide, you need to really understand the details and what is going on. Because used to be, I just pick a problem from the textbook. So the wordings and everything will be exactly the same. And if you just take that thing, and then, I mean, I have problems where I have tried some problem from the book, and I just put it into the Google search bar. The whole thing will come out with solutions. I cannot do that anymore. So there will be a little bit of, so it's going to be, I mean, let me put it this way. It's more like the type of problem you will see after you transfer to a 4-year college. Okay? It's not going to be exceptionally just crazily hard, but it's more like the type of problem that the type of exam you're going to see after you transfer, because they expect you to understand it and somehow put things together. And I usually don't do this, but because of the shelter in place, because it has to be open book and open notes, so I have to do it this way. Don't get too stressed out about this. I'll curve it. Depends on how the class does. Okay? And most of you are doing has a really good grade, high grade in the class now anyway. Right? Because of the second test. A lot of the students do really well on the second test.
Do you have the gradebook somewhere? Because I don't think it's listed in Canvas.
Do I have what? I don't put it on
Right.
campus. I don't put it on campus. But I mean, if you want, you send me an email. I'll let you know how you're doing.
Okay.
Yeah. Yeah. Okay.
All right. Thanks, Professor.
Okay. No problem.
Thank
Bye-bye.
you, Professor.
Okay. Bye. Thank you.